So this is what the replication fork actually looks like, okay? At least to the best of our knowledge. So I'm going to go through the first one slowly because there's a lot of stuff going on here. So here's the helicase. Here's the unreplicated DNA. Here's the leading strand polymerase right here, okay? Here's a polymerase engaged in lagging strand synthesis. And for the purposes of illustration, this is an unengaged polymerase. It's waiting to do the next thing, okay? So what's happening right now is the helicase is unwinding this DNA, creating more template for the leading strand polymerase to just continue moving on. So what you'll see is in all the images I'm going to show you, this just doesn't change at all. The interaction between tau and the helicase is stimulating its activity, and it's holding this whole holoenzyme right where the helicase is, okay? So it's coordinating all that. The lagging strand polymerase has extended a new primer, but as that goes on, there's more single-stranded DNA being generated, and that's being bound by SSB and being kept from folding on itself or interacting with anything else. After this step, for simplicity, I won't be showing the SSB, but keep in mind that SSB proteins would still be there on single-stranded DNA. Okay? Now this is called the trombone model because as you'll see, over time, this loop will get big, and then it will get small. And then it'll get big, and then it'll get small. So people think it looks like a trombone. And actually, there are single molecule studies that show that, in essence, that part of the model is correct. Okay? So what happens next? Well, we've started to accumulate quite a bit of single-stranded DNA here. And in E. coli, basically, once you've accumulated around a kb of DNA, the primase will interact with the helicase and then rapidly synthesize a short primer. Okay? So the next thing that happens is that so during this, we've synthesized more DNA on the lagging strand, but we haven't finished the lagging strand. We haven't gotten to the previous primed Okazaki fragment. And this guy has made more DNA. So technically, this is just getting longer and longer as each one of these images come up. Next thing that happens is that you put a sliding clamp on this single-stranded DNA that has a primer on it. Okay? So this has got to be some pretty good gymnastics going on. You've got a lot of DNA coming from this 1 kb about of DNA between the last primer and, or there's 1 kb between here and here. And so there's probably a lot of flexibility here, but you probably have to do a certain amount of unwinding just to be able to reach around and get that clamp to reach back there. But it then puts a clamp on the DNA, on the primer template junction. Okay? So at that point, the primase is released during that process. And you now have a new sliding clamp at a primer template junction, and you've got this spare polymerase just waiting. Okay? So why would you have a spare polymerase? Why not just wait for the last polymerase to come off? And you know, I can't tell you why, really. I'm not Mother Nature or whoever knows all these things. But one way to think about this is remember what I told you, that it takes a little while for a polymerase to find a new primer template junction. And what I'll tell you is that this whole machine goes at 1,000 base pairs per second. Okay? And it's easy to understand how that would work on the leading strand because I told you you can add a nucleotide every millisecond. So it's basically going full out on the leading strand. But if there's any time required for the lagging strand to find a new primer template junction, which there would be if you had to wait for this polymerase to bind to start this one, you couldn't go that fast because the rate limiting step is almost certainly going to be Okazaki fragment synthesis, not leading strand synthesis. But if you have two polymerases working at the same time, you've got a chance, right? This one can keep going until it reaches the end, but this one will start before that happens. And so you'll have this period where one of them is not engaged, but you won't have a period where neither is engaged, which you would if there were only two polymerases. There would have to be a time between when you release from finishing one template and when you bound the new primer template junction to start a new Okazaki fragment. So does everybody follow the logic? This is the hand-waving logic why you have three polymerases. It could be entirely different reasons, but what's very clear is you do make three polymerase constructs.
Polymerases all the same enzyme?
Exactly the same. So technically, you could even have the leading strand polymerase come off and get on the lagging strand and go around, but there's no reason for this polymerase to come off. And as I said, the processivity is about 50 kb or greater than 50 kb. And what I'll tell you is in a typical E. coli cell, you have a 4 megabase piece of double-stranded DNA. And you have one fork that goes one way, one fork goes the other way, and typically it does 2 megabases without falling off the DNA. Okay? So, generally that's probably not happening. But conceptually, there's nothing different between those three as far as anybody knows. Certainly not the enzyme. So the last thing that would happen here, right, is this would continue, this sort of lagging strand polymerase number 2 would continue moving, okay? And lagging strand polymerase number 1 would have finished its template, and it would then be released and wait for the new primer to be initiated. So we're sort of back to where we started at this point.